Go through the work that I'd assigned you on Thursday, and this will finish up transformation geometry for us doing this. So in question 9, we were asked for each of these diagrams to draw the image of the object under axial symmetry in the given line. So what we're looking to do is we look at each of the points, each of the vertices. How many boxes does it take to get to the line, and do the same number of boxes on the other side for the image. So B takes 4 boxes to the line, which means I must go 4 boxes the other side for the image. C takes 1 box to the line, so 1 box the other side for the image. And of course you'll have used your rulers, but I'm just going to go a bit quickly here. Join the vertices together, and there is our image. Same thing with the letter F, 2 boxes over, 2 boxes over, 5 boxes for C. So 5 boxes for its image, 2 boxes for E, 2 boxes for its image, 5 boxes for B, so 5 boxes for its image, and 5 boxes for A, so 5 boxes for its image. And it's maybe a bit clearer with this that we're getting the mirror image on the other side then. Then we had a more difficult one to consider, okay? So in this case, we want to draw the image of this if I were to fold across this line. So I've gone half a box diagonally here. I must go half a box diagonally the other side to get my image of D. C is also traveling diagonally, 1, 2, and a half. So 1 or half, 1 and a half, 2 and a half to get the image of C over here. 1, 2 and a half, 1 and a half, 2 and a half gives me the image of A. And then finally B, 1, 2, 3, 4 and a half. There's my half, 1 and a half, 2 and a half, 3 and a half, 4 and a half. So more difficult to do one like this where the line isn't straight on, but we absolutely can do it by counting the diagonal boxes we're going through. And there is the image. Now, so hopefully that made sense and you can all do axial symmetry in a line now. Question 10. The diagram shows the isosceles triangle PRQ. The midpoint of RQ is the point M. So this is the halfway point here. They want us to find the image of the following under axial symmetry in the line PM. So we're going to be folding along this line PM. PM is going to be our mirror. That's going to be our mirror line. First, they want us to find the image of R. So R goes 3 boxes over to get to the line and another 3 boxes over. So the image of R is that R maps to Q. So for part A, R maps to Q. This is another way of writing our answers. We can see the image with the little line with the arrow pointing to the image. The image of Q. So Q, when I fold it over, is going to map onto R. So Q maps to R. The image of P. Well, P, when I fold along this line, just gets mapped onto itself. So P maps to P. It's not going to move at all when I fold on that line because it's on the line. Part D, they asked us to see what happens to the line segment MQ. So MQ, when I fold on this line, is going to map onto MR. The M itself doesn't move, but Q moves to R. RP. Now, I don't even need to look at the diagram for this. I can say, well, R will map to Q, and P doesn't move, so this will map to QP. Let's have a look at that. So RP is going to map to QP. Okay, those two sides of the isosceles triangle will end up on each other when I fold over this mirror line. But we can also do it by looking at these facts here. F, the triangle RPM. And again, I'm going to do it using these facts here. R maps to Q, so it's going to map to the triangle Q, P maps to P, and M stays where it is, QPM. So let's look at what that looks like in our diagram. The triangle RPM is this half triangle, and I'm saying that it maps onto QPM, the other side of the triangle, which it does when we fold through that mirror line. And finally, G asked us to where the line segment PM ends up. So again, P doesn't move and M doesn't move. So the line segment PM just maps onto itself when I fold over that line PM. And the last part then, H, the triangle PQR. And again, I'm going to use my facts here and then I'm going to show it on the diagram. P stays where it is, Q maps to R, and R maps to Q. So the triangle PQR maps to the triangle PRQ, which is the same triangle, so it maps onto itself. If you just wrote down PQR here twice, that would be correct as well. It doesn't matter which way round we write those letters. Okay, so that's using a line of symmetry that's halfway through an isosceles triangle. Next, in question 11, we are asked to identify in each diagram the image of the object under a given rotation. So you had done some of these in Wednesday's homework as well. A positive 90-degree rotation around the point O. So here's the point O, and I look at the line that joins the object to O, and it's a positive rotation, which means we're going anti-clockwise by 90 degrees. So that means we're going to end up with this point here, C. So the answer here is that the object maps onto the point C. Next, we have a negative 90-degree rotation, so we're going clockwise. And again, I just look at any side of any point of my object here, and I join the line to O, and I'm looking for a 90-degree rotation here. So my object is going to map onto image 1. A positive anti-clockwise 270, a 3/4 circle rotation about the point O. So if I look at the top of my top vertex of my triangle, I want to go round and round and round until I make a 3/4 circle, or until I've got a 90 degrees left over, and we can see it maps onto the triangle GHI. And finally here, a positive 180-degree rotation. So again, positive anti-clockwise, but it doesn't matter with a 180-degree rotation. We're just going a full half circle. So my object, we look at did we do this already? I think we did. The Santa Claus here is going to go 180 degrees anti-clockwise. So it's going to map onto image 4. Mapping onto image 4. So sorry if that's a repetition of something we've done before. Okay, moving on then to question 12. We're asked to look at this square here, ABCD, and to find the image of the point A under a positive rotation of 90 degrees around the origin. So positive rotation means we're going anti-clockwise. So 90 degrees anti-clockwise from A will bring me to D. Brings me to D. A positive rotation of 180 degrees. So this time I'm completing my line, and we can see that A will map onto C. Once I go 180 degrees, a positive rotation of 270 degrees, another 90 degrees. There's my 3/4 circle, and A now has come 3/4 of the way around to B. And finally, a positive rotation of 360 degrees. We've come full circle, and full circle always brings you back to yourself. So A will map back onto itself. How many different rotations of the square about the origin between 0 degrees and 360 degrees will fit exactly over the object. So if I went through a 10-degree rotation, for example, my square wouldn't fit exactly over the square. But when I do a 90-degree rotation, the first rotation there, where A mapped onto D, D mapped onto C, C mapped onto B, and B mapped onto A, it would fit exactly over the original image. And that will happen whenever we rotate through 90 degrees. So there are only 4 of those because there are 4 90 degrees within 0 and 360. The same question now is being asked for these shapes below here. How many different rotations will have the image fit exactly over itself? Now with a square there was 4, but with this shape, if I go through 180 degrees, it'll end up being upside down. If I go through 90 degrees, it's definitely not going to fit over itself. If I go through 270 degrees, a 3/4 circle rotation, it's definitely not going to fit over itself. In fact, it will only fit over itself if you rotate it through a full circle. But with an equilateral triangle, if I go from here to here, each of my angles is 60 degrees. So if I want to bring A to the next point down here, it will fit over itself because all the sides are the same length. That wouldn't have happened with this one, because if I bring A to B here, it doesn't fit over itself. So to go from A to B here, I've got to go through a rotation of 60 degrees. And I can do the same thing, taking A to C, another 60 degrees, and another 60 degrees would bring me back up here as well. So I can go 180 degrees, will bring A all the way, actually that's only 360 degrees, A to here. I apologize, guys, I should be looking at the rotation around here. So I'm going 180 degree rotation. Of course I am. I'm going through 180 degree rotation, and there are 3 rotations that will bring this shape onto itself. Let's have a look at this one. Is there any rotation which will bring this onto this and also bring this onto this? There isn't, because when I move A, if I twist A around, it's never going to end up on itself until I bring it all the way back to the beginning. This one, however, again, let's label up our points, A, B, C, and D, and consider that when I'm rotating A down to B, it's never going to fit on exactly. But if I rotate A over to C, it will fit on it exactly. So there are, if I go through 180 degrees, of course, sorry guys, I wrote this down wrong, and I've written it down wrong twice. It should be 120 degrees to go from here to here. So if I go through 120 degrees, and I can do that 3 times with my equilateral triangle. With my rectangle, there's only 2 rotations. So with my isosceles triangle, there's only 1 rotation. With my equilateral triangle, there's 2 rotations. With my rectangle, there are 2 rotations. And with my rhombus, no, it's not a rhombus, it's just a parallelogram. I know it's not a rhombus because we aren't told that these 4 sides are the same. A parallelogram is pretty much the same as a rectangle. So let's see. If I were to rotate 180 degrees, I would land here correctly. So 2 rectangle, I wrote 2 rotations, and 2 rotations for shape D as well. Now, don't worry too much about question C. This was just a problem for you to think about and to sort of challenge yourself a little bit. It's not the sort of thing I would put on a test, but I did want you to start thinking about rotations and shapes. So don't worry too much if you couldn't answer this question. Question 13 then. In each case here, identify the transformation. Now, questions 13 and 14 are very much our exam style questions. So it's important that you'd understand what you're being asked to do in these questions and that you could make a decent attempt at them as well. In question 13, identify what type of transformation axial symmetry in the x-axis, axial symmetry in the y-axis, or central symmetry in the origin maps image A onto image B. So A gets mapped onto B if we fold over the y-axis. So axial symmetry in Y. We actually have a shorthand for that, which is SY. D onto C if we do axial symmetry in Y. I'm just going to write it shorthand, axial symmetry in Y. Again, if we fold through the y-axis, D will land on C. A onto D, we have to go through the origin. So that one is central symmetry in the origin. Central symmetry in the origin, 0, 0. And B onto D also has to go through the origin. So again, central symmetry in 0, 0, the origin. So important that you'd understand that, so you need to let me know if you're not understanding what's happening in question 13. Question 14 then. In each question below here, the three images labelled A, B, C are images of this object under some kind of transformation. The transformation could be a translation, axial symmetry, or central symmetry, and we just have to explain what kind of transformation was moved. Now remember, a translation means it looks exactly the same and it's not rotated. An axial symmetry means it's either inverted or reflected, and a central symmetry means both things happened. It's upside down and back to front. So this one is upside down. It's upside down and it's back to front. So this one is a central symmetry. This one is just back to front, so this means it's an axial symmetry. This one looks exactly the same, so it must just have moved, and that's why we get a translation. Now, so from now on, I'm going to just use T for translation, A for axial symmetry, and C for central symmetry. My hippopotamus, this one is back to front, but it's not upside down, so it's just axial symmetry. This one looks exactly the same, it's not, it's just moved, so it's a translation. This one is upside down and back to front, so it is central symmetry. And finally, this graph here, the first image looks exactly the same, it's just moved, so it's a translation. This one is upside down, it's upside down and it's back to front, so it's a central symmetry. And this one is back to front but not upside down, so it's an axial symmetry. Okay, so like I said, questions 13 and 14, they're very, very important. And now all I want you to do today is to make sure you've gone through the solutions of those questions and go over your notes in transformation geometry and let me know if there's any part of it that you're struggling with, that you really don't understand how to do it, and you need to let me know that before we have our test next Thursday. Okay, thank you.